Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Calculus and Curve Sketching. Be sure to be an active learner as you watch this video. As we've seen on numerous occasions, the graph of a function is a useful aid for visualizing the properties. And, in fact, we see much of the calculus that we've learned in graphs like this. For example, we can talk about when is a function decreasing, when is it increasing, when do we have a relative min, when do we have a relative max, when is the function concave up, and when is the function concave down. When it changes concavity, we call that an inflection point. We also have many of the topics that we've talked about before, but now we can speak of them using calculus lingo. For example, we see in this picture both vertical and horizontal asymptotes. But now we know that a vertical asymptote is the limit, as in this picture, x tends to 1 from the right, we go up to infinity, and as x tends to 1 from the left, we go down to minus infinity, and that's going to be the vertical asymptote. But also, we see that as x goes to positive infinity, y gets closer and closer to 1. That's the limit as x goes to infinity is going to be y is 1, and as the limit as x goes to minus infinity is going to be also 1 in this picture. And we see then that both the horizontal and vertical asymptotes can be defined in terms of limits, and calculus is the study of limits. All right, so let's quote those definitions then. A vertical asymptote, the line x equal a, that's a vertical line, by the way, is a vertical asymptote of the graph of a function f if the limit as x tends to a from the right is equal to infinity or minus infinity, or the limit as x tends to a from the left is equal to infinity or minus infinity. And for rational functions being a ratio of polynomials, p of x is a polynomial and q of x is a polynomial, there's a simple criterion to determine whether the graph has any vertical asymptotes, and it's quoted here. So finding vertical asymptotes of a rational function, suppose f is a rational function, that is f of x is equal to p of x over q of x, where both of those are polynomial functions. Then the line x equal a is a vertical asymptote of the graph of x if the denominator q of a is equal to 0, but the numerator p of a is not 0. So what we're going to do is we're going to, in example 1, it says find the vertical asymptotes of the graph of the function y equals f of x equal x squared over 4 minus x squared. Well, the denominator, when is that equal to 0? Well, setting that equal to 0, we factor and we find that that's going to be equal to 0 at plus or minus 2. And the numerator is going to be 4 at both of those places. So we have the denominator being 0 and the numerator not being 0. That tells us these are vertical asymptotes. So x equal 2, that vertical line, and x equal minus 2 are going to be vertical asymptotes. Now what we can do is we can compute the limit as x tends to 2 from the right, and we'll find that that is minus infinity, and as x tends to 2 from the left, and that's going to be positive infinity. Similarly here, when we tend to minus 2 from the right, it's going to be infinity, and from the left is going to be minus infinity. And so there's a graph of that. This graph also shows some horizontal asymptotes, but we're just talking about vertical asymptotes at present. Now it is important that you recall that in order for the line x equal a to be a vertical asymptote, only the denominator can be 0. If the numerator and denominator are both 0, then it need not be a vertical asymptote. For example, and we've talked about this function before, y is equal to 4 times x squared minus 4 all over x minus 2. And if we look at that down here, what will happen is, if I'm trying to find the limit as we tend to 2, first of all, 2 is not in the domain, so we have to have an open circle there. But if we're finding the limit here, we would factor the top, so this would be 4 times x plus 1 times x minus 2. And you see in the limit process the x minus 2's would cancel, and so this function would be what the function would be except at the point 2, and there we're going to have a hole. I know we've talked about this before when we studied limits. Okay, let's move to horizontal asymptotes. The line in y equal b, by the way, the line in y equal b is a horizontal line, is a horizontal asymptote of the graph of y equals f of x if either the limit as x tends to infinity of f of x is b, or the limit as x tends to minus infinity, f of x is equal to b, and b is some constant. So here's an example. We're defining the horizontal asymptotes of the graph of this function. It is y equals f of x equal x squared over 4 minus x squared. Well, if we divide top and bottom, as we did in the limits chapter, by x squared, we're going to get 1 up here, x squared over x squared, and down here we'll get 4 over x squared minus 1. So when we take the limit as x goes to infinity, this part right here will go to 0, so I have 1 over minus 1, which is equal to minus 1. So y equal minus 1 is a horizontal asymptote. And here, note that this happens whether we go to positive infinity or negative infinity. This goes to 0. So if we did the same calculation for negative infinity, we'd also get that. So you see that similarly, x tends to minus infinity, f of x is minus 1 as well. So you see, again, we have a horizontal asymptote, and it is y equal minus 1. It may be noted that it is possible for a graph of a function to have two horizontal asymptotes. One when we're going positive infinity, and the other one as we're going to negative infinity, although that's not the case in this example. We should note that the graph of a polynomial function has no vertical or horizontal asymptotes. That can be seen by a polynomial is the same thing as a polynomial over 1. The denominator is never equal to 0, therefore there are no vertical asymptotes. And if the polynomial's degree greater than or equal to 1, both of these limits, the end behavior goes off to either infinity or minus infinity. Therefore, there are no horizontal asymptotes. Now here's a guide to general curve sketching then. We determine the domain of the function. We find the x and y intercepts of the function. It's easy to find the y-intercept setting x to be 0. Sometimes it's hard to find the y-intercepts because then we're solving f of x equal to 0. Sometimes that is hard. Sometimes it's not. But that is something we can get some points and plot as well. We determine the behavior for large absolute values of x. In your pre-calculus, you called that the end behavior. Here in a calculus course, you would call that the limit as x tends to infinity and the limit as x tends to minus infinity. We would also find the horizontal and vertical asymptotes. We've talked about that here. We're going to determine where f of x is increasing and where f is decreasing. That's properties of the first derivative, being positive or being negative. We can use the first or second derivative test to determine the relative extrema of f. We can use the second derivative to determine the concavity of the function, and we can use the second derivative to also determine inflection points where it changes concavity. And then we can plot some additional points and sketch the graph by connecting the dots. And in fact, we studied in this class, the reason you can connect the dots is the intermediate value property for continuous functions. So this is a nice little summary. Let's take this out on the road and do a couple of problems. So here we're going to sketch the graph of y equals f of x equal x cubed minus 6x squared plus 9x plus 2. Now if you put x to be 0, you see that the y-intercept is 2, and we talk about that here. And so 0, 2 is a point on the graph, and that's where it hits the y-axis. And the domain of this, because the domain of all polynomials is minus infinity to infinity. So we got the first two steps covered. And then we can see what happens as x tends to minus infinity or as x tends to plus infinity, and we see this becomes unbounded. It goes to minus infinity when you're going to minus infinity and to infinity when it is plus infinity. Since it's a polynomial, there are no vertical or horizontal asymptotes. But now we'll start talking about relative maxes and relative mins. Both of those require us to take the derivative. So we take the derivative here, and the derivative of the function is going to be 3x squared minus 12x plus 9 plus 0. And since we know we're going to be setting this equal to 0, this is defined for all values of x. We can factor out the 3. We set it equal to 0, and we find that 1 and 3 are our critical numbers. Now we can use the first derivative test, that's the sign diagram over here, to see what happens when we go across 1 and when we go across 3. So here it tends from positive to negative. That means that's going to be a max. Here it tends from negative to positive, and that's going to be a min. Again, we're going from negative slope to positive, from positive slope to negative slope, and here we're going from negative slope to positive slope. That means that this is a min, that is a max. So we check those, and then we need to know the y values to plot them. So we'll plug in 1 and 3 in there as well. So 1, 6 is the relative maximum, and 3, 2 is a relative minimum. We have a lot of information now, so we start plugging it in. And so we say, oh, there was the relative max, there's the relative min, there's the intercept, and we can, in step 7, set the second derivative equal to 0. The second derivative of this function is going to be 6x minus 12, factor out the 6, so this is 0 when x is equal to 2. Now we can look at the sign graph for f double prime up here, and we can determine that, oh, it is concave up on the interval 2 to plus infinity, and it's concave down on the interval from minus infinity up to 2. So that you see, we know there's the inflection point. We know it's concave down and concave up. And so, and we can also find out what's the y value of that inflection point. So we substitute 2 back in the original function, and we get that that point is 2, 4. That's why we know 2, 4 is the inflection point. So if we summarize all that information, we have all of this. So now we're going to use the intermediate value theorem for continuous functions, and polynomials are continuous, to connect the dots. And this is what the graph looks like at the end of the problem. Pretty good example, huh? Here's example 4, where the sketch graph of y is equal to f of x is equal to x plus 1 over x minus 1. Well, it's undefined when x is equal to 1, so the domain is a set of all real numbers other than x equal 1. If we set y equals 0 here, that means that the numerator is equal to 0, so y equal minus 1 is the, or x equal minus 1 is the x-intercept, and y equal minus 1 is the y-intercept. So we have a couple of points as well. We know where it hits the axis. And then we talk about what is the limit as this goes to infinity, or as this goes to minus infinity. Again, if we divide top and bottom, or look at the ratio of the leading coefficients, we see that they're both 1. So what we can do is we can put this all together, and we can know that these are the horizontal asymptotes. And there is a vertical asymptote, because when is the denominator equal to 0? That's when x is equal to 1. If we take the first derivative, we can see that this is always a decreasing function. There is a minus sign there when we simplify that. So this is always decreasing. So you see it's decreasing here, and it is decreasing here. As x gets bigger, y gets smaller. As x gets bigger, y gets smaller. And if we took a second derivative, we would get this, and the second derivative is in this case, it is going to be 4 over x minus 1 whole cubed. So if you're less than 1, it's going to be concave down. If you're greater than 1, it's concave up. And so there are no candidates for inflection points because the second derivative is never 0. So summarizing all of our facts here, we can graph it in this way. In closing, now more than ever, Time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.